Last month we talked about the damaging effects of water hammer, but there's another state of H2O equally, if not more, dangerous when put in pipes. Hey, I'm Grady. Today on Practical Engineering, we're talking about steam hammer and differential shock. This video is sponsored by Skillshare. More on that later. Unless you live in a home with an older radiator or work in certain industrial settings, you probably aren't as familiar with pipes that carry steam as those that carry water. We don't normally need access to steam in our everyday lives like we do its liquid analog. That's not to say, though, that we don't rely on steam. In fact, it plays a critical role in our modern society. We use steam for heating, cleaning, cooking, and a vast array of industrial processes. About 90% of all electric power produced in the world is through the use of steam turbines. If you didn't see my previous video about water hammer, here are the basics. Water is heavy and incompressible. If you suddenly stop water while it's moving through a pipe, it can create a massive spike in pressure and break stuff, like this pressure gauge. Unlike water, steam is compressible. It's springy and can absorb sudden changes in velocity without a big change in pressure. The danger with steam is when it doesn't want to be steam anymore. In most places on Earth, water exists naturally as a liquid. Under the ambient temperature and pressure conditions we consider habitable, most steam that happens to exist will condense. In a steam pipe, the water that forms from condensation, also known as condensate, is the real danger. And I mean danger in the truest sense of the word. Many lives have been lost in tragic accidents resulting from misunderstanding or misapplication of good engineering principles for steam systems. There are several problems that condensate can cause, and we'll talk about two of them in this video. The first one is thermal shock. Imagine this: you open a valve allowing steam to flow into a steel pipe. As the steam comes into contact with that cold steel, it condenses. The problem is that steam takes up about 1,600 times more volume than its equivalent mass as a liquid. So when it condenses, it literally shrinks. In a closed container like a pipe or this glass bottle that just came out of my microwave, that collapsing steam can lead to catastrophic damage. Water rushes to fill the vacuum created by condensation, cooling the steam even further and creating a runaway situation. This can happen extremely fast, and all that water can accelerate and decelerate violently, hence the name steam hammer. If it's violent enough, it can rupture the pipe, leading to an explosion like the one that happened in New York City in 2007. Check out Nick Moore's video linked below if you want to see this demo in slow motion. Thermal shock is a dangerous form of steam hammer, but it's easy to mitigate. When starting up a steam system, engineers and operators expect condensation as the pipes warm up, so startup procedures will include running at reduced pressure with bleed valves open to make sure that condensation can't form a vacuum. The bigger danger happens during normal operations, but to show how it works, first we need a steam pipe. Condensation in a steam pipe is always occurring just from normal transfer of heat to the outside air, and this is roughly what that might look like. I'm using compressed air here in lieu of steam for the obvious safety implications. Engineers manage this condensate by sloping steam pipes and by installing devices that can get rid of condensate from the pipes called steam traps. Steam traps are a fascinating topic on their own, but occasionally they get clogged or malfunction, allowing condensate to build up. When water and steam flow together in the same pipe, it's known as biphase flow. In this situation, the velocity of the steam is usually much higher than the velocity of the flowing liquid water. If there's only a little bit of condensate in the pipe, that's not really a big deal. But if condensate is accidentally allowed to pool up, things can get dangerous. The steam passing over the top of the liquid can create turbulence and waves. If those waves get high enough, the liquid can create a complete seal inside the pipe with the full pressure of the steam behind it. This seal of water becomes a slug or piston and accelerates down the pipe like the barrel of a cannon, picking up more condensate as it travels. This slug of liquid eventually slams into the end of the pipe, resulting in a dangerous pressure spike known as differential shock. Just like thermal shock, many people have tragically lost their lives in steam pipe explosions caused by this phenomenon. Engineering of steam systems is an incredibly complex topic in mechanical and chemical engineering, and I've just scratched the surface in this video. Whether you realize it or not, many of our modern conveniences are a direct result of steam systems, most notably electricity. So it's critical that engineers can design steam systems to be safe from dangerous phenomena, including thermal and differential shock, also known as steam hammer. Thank you for watching, and let me know what you think. Thanks to Skillshare for sponsoring this video. You probably won't be shocked to learn that Practical Engineering isn't produced by a team of skilled writers, cinematographers, editors, and artists. For the most part, it's just a nerd in the garage, me. And they don't teach this stuff in civil engineering school, so I'm slowly improving my video production skills on my own. Skillshare is an online learning community for creators with more than 17,000 high-quality classes from experts working in their fields. I've been watching the DIY cinematography class by Ryan Booth and using it to improve how I use light and camera angles in my videos. If you're trying to learn a new skill or improve an existing one, click on the link in the description below and start your free trial today. The first 300 people to sign up will get their first 2 months free. Again, thank you for watching, and let me know what you think.